So good afternoon, everyone. I'm Philippe Bonneton. I am a CEMRACS researcher working at Bordeaux University. And my field of research is mainly about dynamics of the nearshore zone, including wave propagation, tidal motions, and also sediment transport and coastal morphodynamics. But today, the talk will be specifically devoted to nearshore hydrodynamics. So what do we call nearshore? It is the zone between the shoreline and extended to the sea water for water depths of over 20 meters. It is a high energy zone which controls exchange between the land and the sea. Exchanges in terms of pollutants, nutriments, and also sediments. So this zone plays a very important role between the land and the sea. So for this region, it is very important to study this nearshore zone. And in this zone, the processes are, hydrodynamics processes and sediment transport processes are most often controlled by wind-generated waves. So wind-generated waves results from the action of wind blowing over the sea surface. In fact, there are two main types of wind-generated waves. Wind sea, in French, mer du vent, where the waves are directly generated and affected by the local wind. You can see a nice example of the sea state during intense storm. And so the waves are relatively random. You can see a sort of chaotic sea state with a broadband spectrum. The second type of wind-generated wave is named swell, houle in French. It corresponds to wind-generated waves that are not directly affected by a local wind. You can see that these waves are very irregular, with a characteristic wavelength. It's not chaotic at all like during a storm. So wind sea and swell are really different. You can see directly on these two photographs. In fact, during a storm, there is, I already said, a broadband spectrum. And due to dispersive effect, I will come back to what is a dispersive effect for wind wave. Due to dispersive effect, wavelengths with large wave with large wavelengths propagate much faster than wave with smaller wavelengths. So this dispersive effect, in fact, reorganize the wave because wave having the same wavelengths travel or propagate at the same celerity. So far away from a storm region, the wave field reorganizes itself into a regular wave, like this one, named swell. Waves have also a strong influence on coastal currents, coastal circulation. And they are one of the most famous current induced by wave is named rip current. It is a narrow current, sort of narrow jet, seaward orientated, which is frequently really intense, sometimes more than 1 meter or 1.5 meters per second. It's very intense. And these rip currents control, in particular, the transfer of sediment from the land to the sea. It is also the major cause of drowning over the world. Another very important current is the longshore current, which is generated when waves are propagating obliquely to the beach. And if the waves are breaking, there is a transfer of momentum flux from wave, and into the breaking, a transfer to momentum of a longshore current. So current in this direction. And this current is very important because it plays a significant role in sediment transport along the beach. So in terms of morphodynamics evolution of the coast, this current plays really a significant role. So wind-generated wave control, in fact, many coastal issues and hazards, in particular related to storm surge, rip current, and coastal morphodynamics and erosion. The main one, perhaps, is storm surge. You can see here very big waves impacting a breakwater, and here waves flooding a coastal city. In Western Europe, and especially in France, the windstorm Cynthia in 2010 caused 59 fatalities and $3 billion euros of damage. So very, very important severe consequences. But during in US, the Hurricane Katrina led to very strong damages, catastrophic damages with 1,500 fatalities, and in terms of building and so on, $125 billion. So certainly the storm surge, flooding induced by storm surge is certainly the main nearshore hazard. But rip currents is also a significant coastal issue. In particular, because it's really dangerous for swimmers. Oops, sorry. You can see swimmers, a strong, intense rip current, seaward oriented, and with some vortices. And you can see that swimmers are caught in this rip. It is important to note that hundreds of drowning deaths each year and tens of thousands of rescues on beaches worldwide. So it's a very significant issue. And it is a leading deadly hazard to recreational beach users. So it's a real problem. Waves also play a significant role for nearshore morphodynamics. For instance, in this figure, you can see an inlet. There is a lagoon, and the open sea is here. You can see the channels, the navigation channels, and sandbars. And in this environment, the dynamics, the evolution of sandbars and navigation channels are mainly controlled by the competition between wind-generated waves, coming like that, and tidal motions. So the competition leading to very strong and intense sediment transport and a morphological evolution. So it's really a severe issue, in particular for navigation safety. Waves also have a significant role in nearshore morphodynamic of sandy beaches. You can see in this figure a nice crescentic shape. We are in the water depth is about 10, 20 meters here. And you can see very nice periodic structures, morphological structure, which result from the interaction between wave-induced currents, and sediment transport, and the coupling between the hydrodynamics and the sediment transport, leading to such a very nice periodic patterns. Such very beautiful patterns, morphological patterns, can also be observed in the intertidal zone of beaches, and also on the shoreline, where you can observe a very nice periodic structure which represents an instability of the morphodynamic state. So the wave control essentially this process. It is also true for coastal erosion. You can see here the impact of erosion very close to buildings. 80 to 85% of the world's shoreline are retreating, so it's a considerable issue, a severe issue. And just an example, coastal erosion in the USA is responsible for approximately $500 million per year, $500 million per year in coastal property loss. So it's relatively significant. So to sum up, wind-generated waves play a significant role in coastal issues and hazard related to storm surge, rip current, coastal morphodynamics and erosion. So it is why it is crucial to understand and predict wave propagation and wave-induced currents in such environments. So it is the main objective of this course. And for understanding a prediction of waves in the nearshore, it's necessary to develop physical approaches, field observation, field laboratory experiments, and physical modeling. But also in parallel, mathematical modeling, analysis, and numerical simulation. So I am a physicist, not a mathematician at all. So my talk today and during the other day will be mainly on the physical approaches. And David Lann will give a complementary talk on the same subject, dealing with the mathematical aspects. And we will try together to discuss about the connection between physical modeling and mathematical modeling. So after this introduction, I will follow this outline. First, I will discuss about wave and briefly about waves and related physical processes. Then I will discuss about modeling of non-breaking wave and modeling of breaking wave. And I will discuss about wave-induced currents, the dynamics of wave-induced currents and modeling in chapter 5. And finally, at the end, some example of long waves, such as tsunami and tidal bores. And finally, some few open questions. So let's go to waves and related physical processes. So you can see here a schematic sketch of the nearshore zone, which can be decomposed in mainly two zones: the shoreline zone, where due to the conservation of energy flux, there is no breaking, and due to the conservation of energy flux, the wave amplitude increases as the water depth decreases. Until the onset of wave breaking, and after that it is the surf zone. After a small transitional zone, the wave reorganize themselves into quasi-periodic bore-like waves, such as in this figure, bores, sort of hydraulic jump in translation. And after the inner surf zone, these bores reach the beach, and it's in the zone which is named the swash zone. So, just an illustration of these different processes. Waves are propagating. You can see here that the wave amplitude is increasing. Here's the beginning of the onset of breaking, and then propagation of such bore. So you see the amplification of wave, beginning onset of breaking, and you can see here bore propagating close to the beach, and this zone of oscillation is named swash zone. So it's a very complicated phenomenon. Indeed, you can see, I would like to discuss about the characteristic scale of processes related to wind-generated wave. For that, I will show you a schematic energy spectrum of cross-shore velocity in the surf zone. So you consider cross-shore velocity at relatively high frequency measurements in the surf zone, and you can see an energy spectrum. So the highest peak, the highest energy peak, is of course related to wind-generated wave, with characteristic period of about 10 seconds. You know, everybody knows such process. So with a frequency of 0.1 Hertz. And in this zone, the waves are really strongly nonlinear. And due to the nonlinearity, there is a transfer of energy from the main peak of energy to the harmonics. So from the first harmonics to the second, third, and so on. And so there is a sort of energy cascade in the wave frequency domain. Of course, in the surf zone, there are waves are breaking and there are intense turbulent motion, and you can observe a typical, classical Kolmogorov law in power minus 5/3. So from the main peak to the turbulence, a real cascade of energy, a large range. But due to the nonlinearity, there is also a transfer of energy from waves, for short waves, for wind-generated waves, to low-frequency waves, which are named infragravity waves. You can see an example of such wave in a diagram where you see the cross-shore, a video with the cross-shore line of pixel and the time evolution. So you can see the trajectory of the waves. You can determine the celerity of each wave. You can see that between each trajectories, it is the characteristic period, relatively short. And you can see the presence of infragravity wave, long period wave, just before the breaking, and also in the swash zone. You have a strong modulation of the wave field, and this process is due to nonlinearities of the shortwave field. Sorry. Of course, I have already explained that there are some wave-induced currents, and these currents, of course, are not stationary. There are some instability, classical hydrodynamic instability, Kelvin-Helmholtz instability, and so on. You can see here really some instability to the jet related to a rip current. And the order of the characteristic period of such instabilities is around 5 to 30 minutes. So in this domain. And also we are most of the time in natural environments with tide. So there are also tidal currents. So a very complicated process ranging from small-scale turbulence scales to large scales related to applications, classical applications in the field. so with characteristic time of a few days and a characteristic scale of about a few tenths of kilometers. So the ratio of characteristic of the scale, large scale to small scale, in time and space is about 100 million. So very complex with a very broad spectrum related to nonlinearities, and all processes are interacting together. So the question is how we can develop tractable modeling for such complicated processes. So if you are interested in small-scale processes, turbulent processes, interaction between turbulence and wave, the impact of wave sharing on wave current sharing on wave, and so on. The suitable approach is certainly based on 3D two-phase flow Navier-Stokes equation. You can see, for instance, an example of a work by Lubin and Glockner, where you can see the impact of a plunging breaker and the generation of transverse vortices. However, such an approach is really limited to small-scale processes and relatively schematic configuration, relatively simple configuration. For real application, we need another approach. The most frequently used approach for coastal application is based on 2D horizontal long wave model. So we have to reduce the complexity of the modeling approach from a 3D Navier-Stokes model to a 2D horizontal long wave approach. So such approaches are based on a ratio between water depth and wavelengths, which is very small, and it is the case for the nearshore zone. So with such an approach, we can simulate explicitly all the frequency spectrum until few days. So it's very nice. Of course, we have not a description of two-phase processes and not an explicit description of the turbulence. So we have to develop and to introduce turbulence parametrization. So after this brief presentation of wave and related physical processes, I will now discuss about modeling of non-breaking waves. So remembering this schematic representation, we have the shoaling zones and the surf zone. So now we will consider the dynamic of wave in the shoaling zone, so just before breaking wave. So in this, so you can see the time evolution of wave elevation at different position in the nearshore zone. Here to plot in the shoaling zone. And what you can observe is that in this zone, the waves are really nonlinear, and that there is a strong horizontal asymmetry. And just before wave breaking, the waves are not breaking here. You can see that the wave is really peaky and skewed, and with a strong horizontal and vertical asymmetry. So objective now for this chapter is to describe modeling strategy for describing these non-breaking processes. So our wave problem is mainly controlled by this three characteristic lengths: the water depth, D, the characteristic amplitude A, and the characteristic wavelength lambda. Zeta is the surface elevation. So Z equals zeta is the parametrization of the free surface. In our approach, for one x position, there is only one zeta value. So wave overturning is not included in our approach. So three characteristic lengths. So the problem is controlled by two-dimensionless parameters. The first one, epsilon, is the ratio of A, the characteristic amplitude, over the characteristic water depth. This parameter is named nonlinearity parameter. And the second one, mu, is related to the ratio of the characteristic water depth over the characteristic length of the wave field. Or K is a wave number. You can write the mu parameter like this. So mu is also named the shallowness parameter. So in the nearshore zone, as you have seen in the previous figure, in particular close to the breaking, the onset of breaking, the wave is strongly nonlinear. And in fact, the epsilon parameter is not small, especially just before the onset of breaking. So it's a parameter of order 1. By contrast, the shallowness parameter in the nearshore zone, so the nearshore for water depth between 20 meters approximately to 0, in this zone, the mu parameter is very small with respect to 1. And we will use this small parameter to develop asymptotic expansion to move from a 3D Euler equation approach to a 2D horizontal model. So zeta is the surface elevation with respect to the state at rest. And D is the water depth at rest. So the equation of the bathymetry is given by Z equals minus D. And the velocity, wave velocity, with two components, two horizontal components, U and V, and one vertical component, W. No, it's very difficult to write equations with PowerPoint, so I shift to Beamer. So the objective now is to derive a well-known model named Serre equation. Serre equation are a 1D model, and the extension to 2D is named generally Serre-Grinaldi equation. So personally, I speak about Serre-Grinaldi equations. So we try to derive this equation only in a 2D vertical plane. Davidan will derive the general case later. But for the sake of simplicity, I prefer to, it's better for me to derive only in a 2D vertical plane, so a 1D horizontal model. So, the basic equations are the Euler equations. So with hydrostatic assumption, very appropriate, totally appropriate for water. So the mass conservation, the divergence of the velocity field is equal to 0. Between the elevation, between the bottom and the sea surface, zeta. You have the two equations for conservation of momentum, horizontal momentum, vertical momentum, and outside the surf zone, the assumption of irrotationality is really good for describing a wave in this environment. So you can see here the irrotational assumption. So of course, later we will use the fact that for such a irrotational flow, the velocity is equal to the gradient of a potential phi. And we need also, of course, some boundary conditions. First, at the free surface. The first one is named Kinematic Equation. To derive this equation is not very complicated. You consider the surface, the free surface, in one point. You consider the normal to this surface, n. And the physical assumption behind this equation is just to consider that the velocity of the surface in itself, us, the projection of the velocity of the surface, us, on the normal, is equal to the projection of the velocity of the fluid particle, n. So otherwise, if this equation is not verified, you can have fragmentation of the free surface. And from this physical assumption, you can derive the first equation, which is named the kinematic equation. We did another boundary condition for the pressure. The pressure is equal at the free surface is the atmospheric pressure. And for the sake of simplicity, we do a variable change by subtracting the atmospheric pressure to the pressure. And so the boundary condition is like that, but it doesn't change the structure of the equations. And the last condition is that the normal velocity with respect to the bathymetry, in this case for flat bottom W, is equal to 0. So I sum up the equation system. And now we will perform a dimensionless analysis, which is the main tool of physicists. We have seen that our wave problem is mainly controlled by two-dimensional parameters. Epsilon, the nonlinearity parameter, and mu, the shallowness parameter. Now we would like to put the whole system of equation into a dimensionless form. For that, we would like to use dimensionless variables for space, horizontal space, vertical, elevation, and so on. And all quantities with prime are of order 1. For that, we divided the quantity x by the characteristic length of variation. So x prime is equal to x divided by L0. The same thing for Z, D0 is a characteristic water depth, and so on for zeta. And for the pressure, we know that in shallow water, the pressure is close to hydrostatic balance. So the hydrostatic balance equation, if we neglect the vertical acceleration, dp dz equal minus density, or 0, g is the gravity. So the order of magnitude for pressure variation over the variation of the water depth d0 is around ρ0 g. So the characteristic pressure variation, the order of magnitude, is ρ0 g d0. It is, and so we use this order of magnitude for the pressure. For the other variables, we have to use the knowledge of the linear theory. So we will see that later. So you have to believe me. And for instance, for the time, the characteristic scale for the time is given by the characteristic velocity in shallow water, which write C root G d0. And so the characteristic time scale is about L0 divided by G d0. And so on. We apply the same thing for the velocity. So now to put the equation in dimensionless form, we replace the dimensional variable x, z, and so on by the dimensionless variables. And I give an example just for the horizontal momentum conservation of momentum. So it's straightforward. You replace, for instance, the du dt. You replace u by its dimensional value, epsilon root g d0, du prime dt prime. T, the order of magnitude of t is L0 root g d0. So up. And so on for each terms. For u du dx, it's very simple, and so on. And you obtain this dimensionless equation. All prime terms are of order 1, and the relative importance of each term is related to the epsilon and mu. So now we have the whole system of equations with the boundary conditions. So for z in the water column, so from -1, which means minus d0 in a dimensional form, to epsilon zeta, which is the position of the free surface. Okay, nothing new. So the next step now is to move from the 3D, or in fact in that case the 2D Euler equation, to 1D depth average equation, to have a more tractable model. So for that, it's relatively straightforward. We integrate over the water depth the mass. Il n'y a pas une brosse? Ah oui. We integrate over depth the mass and the momentum equation over depth. So it's really not complicated. Just for the first one, we integrate this equation. So we found mu integral -1 zeta du dx dz plus the integral of the derivative, so w epsilon zeta minus w minus 1 equal 0. Sorry. Due to the boundary condition at the sea bottom, this quantity is equal to 0. And for this term, we use the Leibniz rule, permuting the derivative and the integral, and you can find and up, oh, should be un terme, minus the derivative of this term, epsilon d zeta dx, u epsilon zeta, plus w epsilon zeta, over mu equals 0. And this quantity is equal to dxhu, where capital U is depth average velocity, 1 over h. So this quantity is equal to the spatial derivative of hu. Everything is exact. And this term is equal to det zeta dt by using the kinematic condition. So you obtain this well-known conserve. So there is no approximation. Is it exact even for strongly nonlinear? It's an exact equation. And we do the same thing for the momentum equation. It is the same. There is no difficulty. And you obtain this equation. So we are looking for a 1D system with two equations based on two variables. The two variables of the problem are zeta and capital U, which is the depth average velocity. So there are two unknown terms, this one and this one. This one is related to the vertical variability of the wave velocity field. So we have to estimate this term. And the other one is related to the integration of the pressure, the derivation, the gradient of the integral of the pressure. So we have to estimate these two unknown terms. For the first one, so first we would like to find a simple expression of this integral as a function of zeta and u. For that, we use the momentum equation in the vertical. So you can see here the epsilon times the vertical acceleration. So it's an exact equation, Euler equation. We can rewrite this equation as minus dp dz equals 1 plus epsilon gamma. Gamma is the vertical acceleration. And then we can integrate this equation like that between z and epsilon zeta. So for integration of 1, okay, epsilon integration of gamma. And using an integral by parts, we found that the integral of p is like that. So we can now estimate the derivative of this integral into two parts. One is epsilon det zeta dx, and the other in function of the vertical acceleration. So this decomposition is very interesting because if the vertical acceleration gamma is negligible in comparison with the pressure gradients on the vertical, this term is negligible, and the derivative of the pressure term is simply a function of zeta, of the derivative of zeta. So this term is a pressure gradient. It's a pressure gradient, and also named hydrostatic pressure gradient because we have done the hydrostatic approximation. But if gamma is not small, you have to take into account this term. So we have divided this unknown term into one known term, this one, the gradient of the hydrostatic pressure, and another unknown. So the equation system can be recast into this new form with the hydrostatic, the gradient of the hydrostatic pressure, and two unknown terms. So to close the system of course is not closed. To close the system, we will use an asymptotic perturbation method based on the small parameters mu. So we perform an asymptotic exponential of the potential function, like that, in a power series in mu. And here we use the mass conservation, du dx, mu du dx plus dw dz equals 0. It is the mass conservation. Replacing u by the gradient of the potential, you obtain this linear equation. With the power series in mu, you obtain this one. And at the first order, you have that the second derivative of phi 0 is equal to 0. So the gradient of phi 0 is a function of x and t. But due to the boundary condition w minus 1 equals 0, the gradient is equals to 0 everywhere. So we can, so we know now that the potential function at orders, at this order, at the lowest order, is equal, for instance, it doesn't depend on z, and is equal, for instance, to psi, which is the potential velocity at the free surface, and so on. So at the next order, you have to solve this equation. Knowing phi 0, you can solve this equation, and you find this relation. And we stop the expansion. We will neglect, in this approach, terms of order mu square. So we have developed the expression for phi. So to obtain the horizontal velocity, you have just to derive phi by x, and you obtain this expression. You can integrate over the vertical small u, and you obtain the depth average velocity, capital U, in function of the velocity potential at the free surface. You can simplify the expression for u by considering that with this equation, you know that dpsi dx equal capital U plus O mu. So mu dpsi dx is equal to mu capital U, mu square. So the term in mu, derivative of psi, everywhere, can be replaced by term with capital U, neglecting term of order mu square. So finally, we obtain the expression for U and W only in function of the depth average velocity and the water depth. So for the horizontal velocity, there is a quadratic evolution and a linear one for the vertical velocity. So we have nearly finished the derivation. It is easy from these two relations to close the system. And for instance, it's straightforward to see that under this approximation, with a small mu parameter, it's straightforward to see that the variability, the term of the variability over the vertical is of order O mu square, so we can neglect this term. And you remember this term is related to gamma, the vertical acceleration. So we can estimate gamma in function, knowing U and W, gamma can be expressed like that. And so finally, we obtain the final system of equations, the Serre equation, the 1D Serre equations. David will derive later the general problem, especially in 2D. So the system is now closed. It is a shallow water equation system. with a nonlinear term, with epsilon, and mu. So mu is really a shallowness parameter, but also it is a parameter which controls, remember, this term, which is a non-hydrostatic pressure terms. So for very small mu parameter, so in very shallow water, or for very long wave, for instance, for tsunami or tide, mu is extremely small, and this term can be neglected. So for tides or tsunami, we can neglect these non-hydrostatic terms. You don't need such Serre equations. But for swell, for wind-generated waves, mu is small, but not so small. So you need these non-hydrostatic terms. And this term play a very important role. In particular, you remember I spoke about the dispersive effect. In fact, this term controls the dispersive effect. Well, perhaps just this one. I would like to conclude with. So you have here the Serre-Grignaldi equation. I have just replaced h, the water depth, by 1 plus epsilon zeta. It is the definition of the water depth, the still water depth plus the elevation of the free surface. And I would like to introduce the dispersive effect, and for that I neglect the nonlinear terms. So you can suppress all terms with a very small epsilon parameter. So you get this linear system, and it is straightforward to obtain this linear system with only one variables just by applying a temporal derivation to this equation. Or equivalently, you obtain this equation for the surface elevation. So if you neglect this term, the non-hydrostatic terms, you get the classical wave equation. The well-known wave equation, which describes, for instance, acoustic wave. So we have a linear problem. So the classical approach is to use a Fourier transform, for instance, of the surface elevation, and to decompose the wave, the unknown wave, with the Fourier decomposition. And you can see here an elementary mode of the Fourier decomposition. Due to the nonlinearity of the equation, we can use the superposition principle to reconstruct the global solution. So it's enough first to study only the dynamics only of the one elementary wave, which writes so a Fourier mode A0 exponential I kx minus omega t. So here it is the phase of the wave, and you can rewrite this equation by with the wavelength of the period is totally equivalent. Of course, for a constant phase, if this phase is constant, the propagation of this phase is straightforward, is equal to omega over k, or equivalently lambda over t. So by definition, this is the velocity phase. If we put this elementary solution into this linear equation, we obtain the dispersion relation like this, which is very interesting because the pulsation is related to the wave number k. And the phase velocity, the definition is there, is here, is equal to this expression. So it is the wave field is dispersive because the celerity of each component k, of each wavelength, the celerity is a function of the wave number or a function of the wavelength. You can see here that the celerity is a decreasing function of the wave number, so an increasing function of the wavelength. So remember at the introduction, waves of large wavelengths are propagating much faster than a wave of smaller wavelength. It's a very important property of wind-generated wave. If you have some questions. C'est ça, hein? C'était à 5 heures. Are there any questions? Yes.
Let us imagine that apart from mathematical modeling, we also care about the security of the real people living near the shores. And we want to know, like, I want to know where to build my house. How much is it secure actually to live? How much is it secure to live near the shore? For this, for me, it seems like I need to know. I need to know the results of modeling of these microscopic effects, like of the turbulence which happen near the shore, because I need to know how dangerous are the waves. But for this, I also know what happens far away in the sea to couple the whole process. I mean, I want to model the whole process from the very beginning of the wave propagation deep in the sea until my house. And my question is, how can we couple both models, like macroscopic and microscopic? Because fundamentally they are really different. The Green-Nagdi model and some turbulent models. And I wonder, how can we couple them to extract some real information, how dangerous it really is to live near the shore?
It's a very, very nice question. So I will discuss this point at the end of my course at chapter 5. It is a very good question because the detail of wave nonlinearities, breaking, and so on is really significant for large-scale nearshore application, but at a short time scale. For wave flooding, or for instance, the dynamic of a tsunami very close to, for very really short time scale, from a few hours to one tidal cycle, 12 hours, something like that.
Yeah, so, and like the mechanical mechanisms, they're really fundamentally different what happens in the sea and what happens near the shore.
So could you repeat your question, please?
I mean, like the fundamental mechanisms which determine how water moves are fundamentally different in the deep sea and near the shore.
Ah, okay. That's what I mean, like, you are speaking about the deep sea. Okay. Deep sea
about like how to couple the deep sea and what's near the shore.
Okay.
Actually, this is the question.
For very large scale application, we need different approaches. We need, for instance, the classical approaches is to, is to use, in fact, a time average wave model, which can be applied in the deep sea to the near shore. We don't model in this, we don't describe the detail of the wave phase. We use large scale there are many models, like operational models such as WaveWatch 3, SWAN, and so on. And so you compute only the time average parameters, mean period, mean energy, and the spatial variation. So it's not in detail.
So it serves like the transition region between the two. And when we're speaking about the transition region, we need some average quantities to couple one.
Yes, it depends on the application. For short time application, such for instance storm flooding induced by a storm, you need a phase resolving modeling approach, as I described today. But for long-term and very large-scale processes, especially for morphodynamic evolution, erosion, the time scale is about several months, several years. So of course, a fast resolving model is not suitable, of course. So in that case, we use a totally different approach with a large-scale wave model, but time average model, with the spatial evolution of the energy of the period. And this model forced a current model, circulation model at very large scale. And the difficulty is to develop the interaction between the. It's
like
another
to transmit data from one to another.
It's another problem. Yes.
All right. Thank you.
Other questions, maybe? No? Okay. So we can thank Philippe for his talk.